Imagine walking the streets of Rome today and standing beneath the towering dome of the Pantheon, a structure so perfectly preserved it could have been built yesterday. Yet this architectural marvel isn't a modern masterpiece. It was poured by Roman hands over 2,000 years ago, while sidewalks and bridges made with today's concrete crack and crumble within decades. Ancient Roman monuments still defy time, their surfaces smooth, their foundations unshaken. What did the Romans know that we've somehow forgotten? The secret lies in their mysteriously durable concrete, a material so advanced it's outlasted empires, wars, and the relentless march of centuries. This isn't just a story about buildings, it's a detective story, one where scientists and historians are racing to crack a code left behind by ancient engineers. For years, researchers assumed Roman concrete was strong simply because of volcanic ash, a key ingredient mixed into their recipes, but recent discoveries have revealed something far more fascinating. Hidden within these ancient walls are microscopic structures that actively heal cracks, like a living material repairing itself. The Romans didn't just build to last, they built to regenerate, and the implications for our modern world are staggering. So how did they do it? What lost techniques allow their concrete to thrive in salt water, withstand earthquakes, and even grow stronger with age? The answers lie in a blend of brilliant engineering, accidental chemistry, and natural materials harnessed in ways we're only beginning to understand. In this video, we'll unravel the scientific secrets buried in Roman concrete, from the surprising role of seawater in its strength to the self-healing minerals that modern scientists are scrambling to replicate. By the end, you'll see these ancient structures not as ruins, but as time capsules holding blueprints for a more resilient future. The Romans may have left us their roads and aqueducts, but their greatest gift might just be the recipe for a concrete that could revolutionize how we build tomorrow. Take a look at modern concrete structures around you: sidewalks with jagged fractures, bridges requiring constant repairs, dams with worrying cracks creeping through their walls. Some start deteriorating within 50 years, while others crumble alarmingly after just a few decades. Now shift your gaze to the Roman aqueducts still standing after 2 millennia, or the Colosseum skeletal arches that have endured earthquakes, invasions, and the weight of centuries. The difference isn't just striking, it's baffling. How could an empire without modern chemistry, without precision machinery, create a building material that outperforms our own? The Romans didn't just stumble upon this formula by accident. Their concrete was a deliberate masterpiece, crafted through meticulous observation of natural materials and refined over generations. While we rely on Portland cement, a brittle high-energy product invented in the 1800s, they mixed volcanic ash, lime, and chunks of volcanic rock, creating a material that didn't just resist erosion but thrived in it. Even more astonishing, some of their maritime structures, like the harbor at Caesarea, grew tougher over time as seawater reacted with the concrete, forming minerals that filled microscopic cracks. This leaves us with a humbling question: what if the Romans understood Earth's chemistry better than we do? Modern concrete fails because it's designed to be static, unchanging. But Roman concrete was dynamic, almost alive, adapting to its environment. As scientists now analyze ancient samples with advanced tools, they're uncovering a truth that rewrites our assumptions about durability. The Pantheon's dome, the piers of Roman harbors, the roads still buried under modern cities, they aren't just remnants of the past. They're silent teachers, holding lessons we're only beginning to decode. The story of Roman concrete begins long before towering domes and sprawling aqueducts. It starts with simple, practical needs. Around the 3rd century before the Common Era, builders in the growing Roman Republic stumbled upon a revolutionary mix that would change architecture forever. They called it opus caementicium, meaning stone-like work, and it wasn't just stronger than the rubble and mortar constructions of their neighbors. It was transformative. Picture the Mediterranean world at this time. Cities were expanding, trade routes demanded sturdy ports, and ambitious leaders wanted monuments to outlast them. Ordinary mortar couldn't handle the stress, but this new material, a blend of volcanic ash, lime, and crushed rock, could be poured into molds, set underwater, and even hardened over time. By the 1st century of the Common Era, Roman engineers had perfected the recipe. The Pantheon's dome, still the largest unreinforced concrete dome in existence, wasn't just a display of grandeur. It was a testament to centuries of experimentation. Unlike modern concrete, which relies on steel reinforcements to prevent collapse, Roman concrete achieved its strength through chemistry. The volcanic ash they used, particularly from the Pozzuoli region, reacted with lime and water to form a glue-like binder that resisted cracks. Even more remarkably, they adjusted mixes for different purposes: lighter volcanic stones for the Pantheon's soaring ceiling, denser blends for harbor walls battered by waves. What's often overlooked is how democratized this material was. From the grandest temples to humble tenements, concrete reshaped daily life. Aqueducts delivered water across valleys, amphitheaters hosted tens of thousands, and roads knitted the empire together, all because of this versatile, durable substance. While other civilizations built with stone or mud brick, Rome built with a material that adapted, endured, and in some ways improved with age. The secret wasn't just in the ingredients, but in the mindset. They didn't just build structures, they engineered legacies. At the heart of Roman concrete's legendary durability were three simple ingredients: volcanic ash, lime, and water. But don't let the simplicity fool you. This was no ordinary mix. The volcanic ash, known as Pozzolana, was the game changer. Harvested from the fiery slopes near Pozzuoli in southern Italy, this fine, rust-colored powder contained minerals unlike anything found in modern cement. When combined with lime, burned limestone that acted as a glue, and water, a chemical reaction would begin that hardened not just for days, but for centuries. Modern Portland cement, invented in the 1800s, relies on high-temperature processing that creates a rigid but brittle structure. Roman concrete worked differently. The Pozzolana's secret lay in its high concentration of silica and alumina, compounds that reacted with lime to form a gel-like substance. This gel didn't just bind the mixture, it seeped into cracks over time, filling gaps and reinforcing weak spots. Imagine a broken bone healing stronger at the fracture point. Roman concrete did something similar, growing more resilient under stress, but the real marvel was how this mix behaved underwater. While modern concrete crumbles when exposed to seawater, Roman harbor structures thrived in it. The saltwater triggered a slow reaction, producing rare minerals like a luminous tobermorite within the concrete's matrix. These needle-like crystals interlaced like microscopic armor, resisting erosion while making the material tougher with each passing wave. Modern scientists have spent decades trying to replicate this self-healing property, only to realize the Romans had mastered it 2,000 years ago without labs, without microscopes, just by observing nature's raw materials and harnessing their hidden potential. What's even more striking is how carefully the Romans selected their ingredients. Pozzuoli's volcanic ash wasn't the only option, but it was the gold standard, shipped across the empire for critical projects. Builders knew that using inferior ash or skipping the meticulous mixing process could doom a structure to fail. This wasn't guesswork, it was precision engineering disguised as simplicity, a recipe refined through generations of trial and error. Today's concrete may set faster, but time has proven which formula truly stands the test of centuries. The magic of Roman concrete wasn't just in mixing ingredients, it was in the alchemy of their volcanic ash. Modern cement relies on Portland cement's rigid structure, which forms tight bonds but cracks under pressure like dried clay. Roman Pozzolana worked differently. Its secret weapon, aluminosilicate, a compound abundant in the ash from Mount Vesuvius and other Italian volcanoes. When this fine powder met slaked lime and water, a slow-motion chemical dance began. Over weeks and months, the mixture transformed into a glue-like gel called calcium aluminum silicate hydrate, or CaSH for short. Picture honey seeping into cracks and hardening. That's what this gel did, seeping into every pore and crevice, creating a bond that didn't just resist cracks but flexed with them. Modern cement, by comparison, is like a pane of glass. It sets quickly through a high-temperature process that creates stiff, brittle crystals. When stress hits, whether from shifting ground or freezing temperatures, these crystals snap, leaving fractures that spread like spider webs. Roman concrete behaved more like cartilage, bending slightly under pressure, while its CaSH gel constantly filled microfractures with new minerals. This self-healing property came from the aluminosilicate's unique structure. Under an electron microscope, modern cement shows orderly but fragile crystal patterns, while Roman concrete reveals a chaotic, web-like matrix, messy but far more resilient. The brilliance of Roman engineers lay in their choice of specific volcanic deposits. Not all ash worked equally. Pozzuoli's Pozzolana contained high levels of reactive silica and alumina, along with trace metals like iron that boosted the curing process. Builders even adjusted recipes based on location, using coarser ash for bulkier structures or finer powder for delicate arches. They didn't know the atomic details, but centuries of observation taught them which volcanic slopes yielded the strongest results. Today's scientists, armed with spectrometers and particle accelerators, have confirmed what the Romans intuited. This ash wasn't just filler. It was the catalyst for a chemical reaction that turned humble mortar into a time-defying marvel. Perhaps the most striking difference lies in how these materials age. Modern concrete degrades as water penetrates cracks, rusting steel reinforcements and expanding fissures. Roman concrete exposed to seawater in harbors like Portus did the opposite. Saltwater reacted with leftover lime and ash to form rare minerals like aluminous tobermorite, a crystalline reinforcement that made the concrete denser over centuries. While our docks crumble within decades, Roman piers endure as jagged reefs beneath Mediterranean waves. Their strength, hidden in chemistry, we're still struggling to replicate. The lesson isn't just in the recipe, but in the philosophy. Sometimes the strongest bonds aren't rigid, they're adaptable. Think of slaked lime as the quiet conductor of this ancient chemical orchestra, unassuming but utterly essential. The Romans didn't just toss limestone into a fire. They mastered a meticulous process that transformed brittle rock into the glue holding their empire together. First, they heated limestone to nearly 900 degrees Celsius in massive kilns, a temperature so extreme it forced the stone to shed carbon dioxide, leaving behind quicklime, a volatile, caustic powder. But here's where their ingenuity shone. They didn't stop there. Quicklime alone would have been useless, even dangerous, reacting violently with water. So they slaked it, carefully adding water to trigger a fiery reaction that produced calcium hydroxide, a stable paste with unique properties. This slaked lime became the backbone of Roman concrete's chemical magic. When mixed with volcanic ash and water, it didn't just harden, it initiated a slow, transformative reaction. Over months or even years, the calcium hydroxide seeped into the Pozzolana's silica-rich particles, creating interlocking crystals and gel-like structures that bound everything together. Modern cement skips this patience testing process, relying instead on rapid-setting compounds that sacrifice long-term resilience for speed. The Romans, though, understood something profound. True strength couldn't be rushed. What's often overlooked is how they tailored lime for different environments. In maritime structures like the harbor at Caesarea, builders used lime with higher impurities, trace metals like magnesium or iron, which actually enhanced the concrete's reaction with seawater. On land, they opted for purer lime to ensure smoother finishes on monuments. This wasn't haphazard, it was chemistry refined through observation. They even recycled leftover lime chunks, embedding them into new mixes as lime clasts, tiny reservoirs of reactivity that 2 millennia later, scientists discovered were key to the concrete's self-healing properties. When cracks formed, water activated these clasts, releasing fresh calcium hydroxide to seal gaps like microscopic stonemasons. The brilliance of Roman lime lies in its duality. It was both glue and guardian, binding the mix while standing ready to repair itself. Today's concrete, for all its technological advancements, lacks this dynamic quality. We've traded the slow wisdom of slaked lime for the immediacy of Portland cement, and the cracks in our infrastructure tell the story. The Romans didn't just build with lime, they harnessed its living chemistry, proving that sometimes the most unassuming ingredients hold the greatest power. If modern engineers shudder at the thought of seawater touching concrete, the Romans would have laughed. While saltwater erodes today's harbors like acid on metal, their maritime structures performed a magic trick. They grew stronger underwater. The key lies in a paradox where modern concrete fails. Roman concrete thrived because of the very thing that should destroy it. Take the ancient harbor of Portus, built by Emperor Claudius near Ostia. 2,000 years later, its submerged concrete blocks remain intact, their surfaces roughened but their cores harder than the day they were poured. Meanwhile, modern seawalls nearby deteriorate within decades, their steel reinforcements rusting, their surfaces flaking like old paint. The difference hinges on chemistry. Modern Portland cement forms rigid bonds that seawater slowly dissolves, seeping into cracks and corroding steel reinforcements. Roman concrete, though, contained no steel and no weak bonds to attack. Instead, seawater triggered a second life in their mix. When saltwater penetrated the concrete, it reacted with leftover lime clasts and volcanic ash, creating rare minerals like aluminous tobermorite and stratlingite. These needle-like crystals spread through the material like microscopic scaffolding, filling voids and reinforcing weak points. The more seawater interacted with the concrete, the denser and tougher it became, a process scientists now call post-pozzolanic reactivity. It's as if the Romans designed a material that evolved to fight its greatest enemy by turning it into an ally. Recent studies at the University of Utah revealed just how brilliantly this worked. Using advanced X-ray microscopy, researchers found that Roman marine concrete developed a layered structure over centuries. The outer crust, battered by waves, became slightly porous, but this porosity acted like a sacrificial layer, absorbing energy while the inner core grew ever more resilient. Modern concrete, by contrast, fails catastrophically once cracks reach its steel skeleton. The Romans engineered their material to distribute stress, not resist it rigidly, much like how bamboo bends in a storm instead of snapping. Perhaps the most startling insight came from analyzing concrete chunks from the ancient harbor of Caesarea in Israel. Samples showed that seawater had percolated nearly 20 centimeters deep over 2 millennia, yet instead of causing damage, it left behind an intricate lacework of strengthening minerals. Modern marine concrete, even with protective coatings, rarely lasts a century without major repairs. The Romans didn't just outbuild us, they outsmarted time itself by designing a material that embraced corrosion rather than fearing it. Their concrete wasn't just durable, it was anti-fragile, thriving under conditions that would doom our best efforts today. This raises a provocative question. Did Roman engineers intentionally exploit seawater's effects, or was this resilience a happy accident? Evidence suggests they knew exactly what they were doing. Vitruvius, the famed first-century architect, specifically recommended volcanic ash from coastal regions for maritime projects, noting its superior resistance to the assault of the waves. Builders at Portus and Caesarea also used coarse, porous aggregates, creating pathways for seawater to penetrate and trigger beneficial reactions. They may not have understood atomic structures, but centuries of observation taught them that seawater wasn't a destroyer, it was a co-builder. Today, scientists are racing to replicate this ancient alchemy. At laboratories from Berkeley to Cambridge, teams are testing modern versions of Roman concrete in saltwater tanks, hoping to unlock its self-healing properties for seawalls, offshore wind farms, and even radioactive waste containment. Early results are promising, but there's irony in the pursuit. We're spending millions to reinvent what the Romans perfected with volcanic ash, lime, and seawater, ingredients they sourced for pennies. Their greatest innovation wasn't just a recipe, it was a philosophy. Instead of fighting nature's forces, they harnessed them, creating a legacy not just in stone, but in the very chemistry of resilience. The enduring lesson here isn't about materials, it's about mindset. Modern engineering often seeks to conquer environmental challenges with brute strength, thicker walls, more steel, synthetic sealants. The Romans worked with nature's grain, designing structures that adapted and improved under stress. Their concrete didn't just survive the sea, it collaborated with it, turning a corrosive enemy into a silent partner in longevity. As climate change accelerates, coastal erosion and rising sea levels threaten infrastructure globally, their 2,000-year-old harbors stand as quiet mentors, reminding us that sometimes the strongest solutions don't resist nature, they dance with it. In 2017, a team of researchers at UC Berkeley made a discovery that flipped modern concrete science on its head. Using advanced imaging techniques like X-ray microdiffraction and electron microscopy, they peered into the atomic structure of Roman harbor concrete, and what they found shocked them. Embedded throughout the ancient material were tiny, needle-like crystals of aluminous tobermorite, a mineral so rare it's almost never found in nature. Even more surprising, these crystals weren't part of the original mix. They'd grown over time like invisible stitches, healing microscopic tears in the concrete's fabric. And the catalyst for this self-repair, seawater, the very substance that corrodes modern concrete within years. The process works like a slow-motion alchemy. When seawater seeps into Roman concrete, it reacts with leftover lime clast, those small, white flecks of unreacted calcium hydroxide scattered through the material. This triggers a chain reaction. The lime dissolves, releasing calcium ions that bind with silica from the volcanic ash. Under the seawater's influence, these elements reorganize into a luminous tobermorite, a mineral with an interlocking crystal structure that's stronger than the original binder. Imagine pouring water onto a cracked sponge, only to watch the liquid transform into reinforcing fibers that knit the gaps together. That's essentially what happens at a microscopic level in these ancient walls. What makes the Berkeley study so groundbreaking is how it challenges modern assumptions about durability. Today's engineers aim to create concrete that's impervious to water, sealing it with coatings and waterproof additives. The Romans did the opposite. Their concrete was designed to breathe, allowing seawater to penetrate deep into its matrix. Far from weakening the material, this exposure activated a kind of molecular backup system. Microcracks became pathways for mineral-rich solutions, ensuring that any damage prompted a repair response. It's a stark contrast to modern marine concrete, where a single crack can become a runaway failure as saltwater rushes in to corrode steel reinforcements. The study also revealed something even more counterintuitive. Time was the Romans' secret ingredient. While modern concrete achieves most of its strength within 28 days, Roman concrete kept evolving for centuries. Samples from the ancient harbor of Portus showed that luminous tobermorite crystals became more abundant in areas exposed to constant wave action. This wasn't a flaw, it was a feature. The concrete's initial mix was deliberately underreacted, leaving reservoirs of lime and silica that could activate when needed. Like a tree adding growth rings, the material adapted to its environment, growing more complex and resilient with each passing decade. Perhaps the most humbling insight came when researchers tried to replicate the effect in the lab. Even with precise measurements and controlled conditions, their modern versions couldn't match the Roman concrete's crystalline complexity. The ancient material had benefited from variables impossible to simulate: centuries of temperature fluctuations, the mechanical stress of tides, and the slow infusion of seawater minerals. It's a reminder that some engineering solutions can't be rushed. They require the patient collaboration of chemistry and time. This discovery has sent shockwaves through the construction industry. Suddenly, the idea of self-healing concrete, a futuristic concept just a decade ago, seems not only possible but modeled perfectly by ancient builders. Companies are now racing to develop modern versions using synthetic tobermorite or bacteria that secrete calcite. Yet the irony is palpable. The Romans achieved this 2 millennia ago with nothing more than volcanic ash, lime, and a deep understanding of nature's rhythms. Their concrete didn't fight the sea, it invited the sea to become part of its strength. In an age of climate change and crumbling infrastructure, that lesson feels more vital than ever. The cracks in Roman concrete didn't spell doom, they sparked regeneration. Picture this: a tiny fissure forms in a 2,000-year-old harbor wall, barely visible to the naked eye. Seawater trickles in, carrying dissolved minerals. Instead of widening the gap, something miraculous happens. The water reacts with lime particles hidden in the concrete, creating a glittering lattice of new crystals that knit the fracture closed. This wasn't just repair, it was rebirth, a built-in healing mechanism modern engineers refer to as living concrete. While today's structures degrade with every crack, Roman architecture treated damage as an invitation to grow stronger. The science behind this self-healing phenomenon reads like something from a futuristic novel. When cracks form, water activates dormant lime clasts, tiny white flecks of calcium hydroxide left deliberately in the mix. These clasts dissolve, releasing calcium ions that react with silica from the volcanic ash. The solution crystallizes into minerals like strettlingite and luminous tobermorite, filling gaps with a network tougher than the original material. Imagine a cut on your skin healing not with a scar, but with reinforced tissue. That's precisely what happened in Roman concrete, where every injury prompted a molecular upgrade. Modern attempts to replicate this have led to some extraordinary innovations. Researchers at Delft University created a bioconcrete infused with limestone-producing bacteria that awaken when water enters cracks. Others are experimenting with synthetic polymers that expand when exposed to moisture. But these solutions require carefully engineered additives, special capsules, or delicate microbes. The Romans achieved self-healing with nothing more than volcanic ash and a clever understanding of chemistry. Their concrete wasn't just mixed, it was designed with built-in redundancy, like a smartphone that repairs its own shattered screen using ambient humidity. What's even more astonishing is how this healing process improved over centuries. Core samples from the Portus Harbor show that older concrete contains more of these reinforcing crystals than younger sections. The material didn't just maintain itself, it evolved, adapting to stressors like a tree strengthening its trunk against wind. Modern concrete, by contrast, follows a one-way path to degradation. Once cracks breach its waterproof coatings, the race against collapse begins. Roman builders embraced permeability, creating structures that welcomed environmental interactions as opportunities rather than threats. The implications for today's infrastructure are profound. Imagine bridges that repair their own stress fractures during rainstorms, or subway tunnels that seal micro-cracks with minerals drawn from groundwater. This isn't science fiction, it's ancient wisdom waiting to be reclaimed. The Romans didn't have microscopes or chemical formulas, but their empirical mastery of materials gave us a blueprint for resilience we're still struggling to decode. Their concrete didn't fight time, it collaborated with it, turning the inevitable wear of centuries into a process of continual renewal. Perhaps the most poetic lesson lies in how these ancient structures communicate their secrets. When scientists examine Roman concrete under electron microscopes, they don't see a static relic, they witness an ongoing chemical conversation, a dialogue between human ingenuity and natural forces that's been unfolding for millennia. Every crack tells a story of recovery, every mineral deposit a testament to patience. In our era of disposable materials and planned obsolescence, these silent ruins whisper a radical idea: the best things we build shouldn't just endure. They should learn how to heal. For centuries, the secret behind Roman concrete's self-healing properties seemed lost to time, until scientists took a closer look at those tiny white flecks speckled throughout ancient samples. In 2023, a groundbreaking study from MIT flipped the script entirely. Researchers discovered that Roman builders weren't just mixing lukewarm mortar, they were working with scorching hot quicklime, a technique now called hot mixing that gave their concrete an almost magical ability to repair itself. Picture a blacksmith plunging red-hot metal into water. That same explosive reaction was happening in their mortar pits, creating tiny, reactive lime chunks that became the material's hidden healing agents. Here's how it worked. Instead of using pre-slaked lime paste like modern builders, Roman engineers tossed chunks of quicklime, freshly burned limestone at near melting temperatures, directly into the mix with volcanic ash and water. The result, a violent chemical dance. The quicklime fractured into micro-scale particles, some reacting instantly to form the binder, while others remained trapped like dormant capsules inside the hardening concrete. These unreacted lime clasts, once dismissed as sloppy mixing, turned out to be the material's genius failsafe. When cracks formed centuries later, water seeped in, waking up these lime particles. Like miniature repair kits, they dissolved and recrystallized, stitching fractures shut with fresh mineral bonds. The MIT team dubbed this the popsicle effect. Just as a frozen treat stays cold long after leaving the freezer, these lime clasts retained their reactive potential for millennia, ready to activate at the first sign of damage. Modern concrete, by contrast, uses fully slaked lime paste, leaving no reserves for future repairs. Once it cracks, the damage spreads unchecked, but Roman concrete had a built-in insurance policy, its healing capability embedded right into the original recipe. The hotter the initial mix, the more of these reactive particles formed, a detail confirmed by analyzing ancient samples with nanoscale X-ray imaging. What's even more impressive is how precisely the Romans calibrated this process. Too much quicklime, and the mix could overheat, crumbling from thermal stress. Too little and the self-healing effect weakened. Their solution, volcanic ash, acted as a natural temperature regulator, its high silica content absorbing excess heat while ensuring even distribution of lime clasts. This delicate balance wasn't accidental, it reflected generations of refined craftsmanship. Modern labs can now replicate it, but only with precise measurements and controlled conditions. The Romans achieved it with fire, intuition, and an intimate knowledge of materials. The implications are staggering. Imagine a future where bridges embed similar lime reservoirs, or basement walls that seal their own leaks after a storm. MIT's team has already prototyped modern versions, proving that hot mixing isn't just a historical curiosity, it's a viable path to resilient infrastructure. Yet there's irony in our rush to patent this innovation. The real breakthrough happened 2,000 years ago when anonymous Roman laborers tending smoky lime kilns unlocked a secret we're only now appreciating. Their concrete didn't just resist time, it carried the tools for its own immortality, hidden in plain sight as flecks of white dust waiting for water to whisper them back to life. Picture two concrete blocks, one freshly poured at a modern construction site, the other pulled from the ruins of a Roman dock. At first glance, they might look similar. But time tells wildly different stories. That modern block will start showing wear within decades, its surface cracking as internal steel rusts, while the Roman sample remains intact after 20 centuries of storms, waves, and salt water. This isn't just a difference in longevity, it's a clash of philosophies. Modern concrete prioritizes speed and initial strength, setting hard within hours to meet construction deadlines. Roman concrete played the long game, its slow chemical reactions yielding a material that outlived the empire that created it. The numbers speak volumes. A typical modern concrete structure lasts 50 to 100 years before requiring major repairs or replacement. The Pantheon's dome, built in 126 of the Common Era, hasn't needed structural reinforcement in nearly 2,000 years. Boston's Big Dig tunnels, completed in 2007, started leaking within a decade. Meanwhile, the Roman breakwater at Caesarea still protects Israel's coast after 2 millennia. This staggering gap isn't just about material science, it's rooted in environmental consequences. Producing modern Portland cement requires heating limestone to nearly 1,500 degrees Celsius, a process that guzzles energy and accounts for roughly 8% of global carbon dioxide emissions. Roman concrete, by contrast, was shockingly low-tech. Their lime kilns operated at 700 degrees Celsius cooler, cutting energy needs dramatically. Volcanic ash, the key ingredient, required no processing beyond grinding. Nature had already done the work. Even the shipping was sustainable. Builders often source materials locally, like the Pozzolana from Italy's volcanic fields. Modern concrete's carbon footprint balloons further from transportation, with aggregates hauled cross-country and cement shipped globally. The Romans essentially practiced circular economy principles by default, using regional resources with minimal processing. Maintenance tells another damning tale. Modern infrastructure becomes a money pit almost immediately. America's concrete bridges need $63 billion in repairs just to remain functional. Roman roads, laid without a single steel bar or synthetic sealant, still form the foundation of highways across Europe. Their secret, avoiding the fatal flaw of modern reinforced concrete, steel's tendency to rust. When water penetrates today's structures, it corrodes the rebar inside, causing catastrophic concrete cancer as expanding rust bursts the material apart. Roman engineers sidestepped this entirely by designing compression-based structures that needed no metal reinforcement. Perhaps the most overlooked advantage lies in adaptability. Modern concrete is rigid and brittle, prone to catastrophic failure when overloaded. Roman concrete flexed slightly under stress, its volcanic ash matrix redistributing force like a shock absorber. Earthquakes that toppled contemporary buildings barely left cracks in Roman temples. Even more remarkably, their marine concrete wasn't just resistant to seawater, it exploited saltwater's chemistry to grow stronger. While modern harbors spent fortunes replacing corroded pilings, ancient Roman piers evolved into stone reefs, their mineral structures denser now than when first submerged. The contrast couldn't be starker. We've created a material that demands constant care, spews carbon, and dies young. They engineered one that heals itself, slashes emissions, and laughs at time. As climate change accelerates infrastructure decay worldwide, the irony stings. Our most advanced concrete is embarrassingly primitive compared to an empire that built with volcanoes and intuition. The real question isn't why Roman concrete lasted millennia, it's why we ever stopped making it. The Pantheon's dome isn't just an architectural marvel, it's a silent revolution in concrete engineering, suspended in midair for nearly 2,000 years. No steel reinforcements, no modern adhesives, just a perfect hemisphere of Roman concrete stretching 43 meters across, a record it held until the industrial age. What's even more astonishing is how it achieves this feat, not through brute thickness, but through ingenious design and material alchemy. The dome's secret lies in its graduated layers, each meticulously tailored to balance strength and weight. At its base, the concrete is nearly 6 meters thick, packed with dense travertine aggregate, but as the curve ascends, the mix transforms volcanic tuff and pumice lighten the load, while the very top uses porous volcanic foam, some pieces no heavier than cork. It's as if the Romans sculpted gravity itself, thinning the dome's skin to a mere 1.5 meters at the oculus, the open circle that crowns the space. Engineers still debate how this structure defied collapse. Modern analysis reveals two critical innovations. First, the dome isn't pure concrete. Embedded within its matrix are hidden, relieving arches, brick ribs that redistribute weight like the spokes of a bicycle wheel. These weren't decorative, they acted as a skeletal system, channeling stresses downward through the Pantheon's drum-shaped walls. Second, the concrete wasn't poured all at once. Roman builders worked in horizontal sections, allowing each layer to partially set before adding the next. This created a monolithic structure without the cracking that plagues modern single-pour domes. The result, a building that survived earthquakes, invasions, and even the removal of its original bronze roof without so much as a structural tremor. But the real magic lies in the material's composition. Samples drilled from the dome show a high concentration of Pozzolana from the Alban Hills, a volcanic region east of Rome. This particular ash reacted with lime to form a binder with exceptional tensile strength, a quality most ancient concretes lacked. Even more remarkably, the mix included ground terracotta, a detail often overlooked. Recent studies suggest this additive created microscopic pores, allowing the dome to breathe as temperatures fluctuated, preventing the thermal stress cracks that doom modern concrete structures. The oculus plays a role too. Far from being just a symbolic connection to the heavens, this opening reduces wind load and acts as a natural stress relief valve, dispersing energy that might otherwise fracture the dome. Perhaps the most telling detail is what's missing. Unlike later Renaissance domes, the Pantheon has no chains or tension rings to counteract outward thrust. Its stability comes entirely from the concrete's compressive strength and the precise geometry of its curves. The Romans understood something modern engineers often forget. Sometimes the strongest shape isn't the one that resists forces, but the one that guides them. Every ounce of weight in the Pantheon flows seamlessly down the dome's ribs, through the walls and into the earth, a kinetic sculpture in slow motion. What modern laser scans reveal is even more extraordinary. The dome's interior coffers, those iconic sunken panels, aren't just decorative. They precisely thin the structure where stresses are lowest, shaving thousands of tons without sacrificing integrity. Even the aggregate size follows a pattern, with larger stones at the base giving way to finer particles near the top. This wasn't guesswork, it was precision engineering on a scale we've only recently begun to quantify with finite element analysis. The Romans achieved it through intuition, observation, and perhaps most importantly, a willingness to let the material speak for itself. Today, the Pantheon stands as both a monument and a laboratory. Its concrete, still pristine after 2 millennia, contains clues we're only beginning to decipher. In 2015, researchers discovered nanoscale stretlingite crystals within samples, a mineral that forms when a luminous tobermorite reacts with lime over centuries. These crystals create a self-reinforcing lattice, effectively making the dome stronger now than when Hadrian's architects completed it. While modern concrete decays, the Pantheon's concrete evolves, its chemistry still quietly at work. The lesson here isn't just about domes or even concrete. It's about designing with time as an ally rather than an enemy. The Romans didn't just build for their generation, they engineered for eternity, and their masterpiece still whispers its secrets to those who listen. Off the coast of modern-day Anzio lies one of Rome's most extraordinary engineering triumphs, Portus Cassanis, a harbor complex that sank beneath the waves 2 millennia ago, yet whose concrete piers stand today as jagged underwater monuments. While modern marine concrete crumbles within decades under seawater's corrosive touch, these ancient structures tell a different story, their secret. A deliberate collaboration with the ocean itself. When Roman engineers poured these piers in the 2nd century before the Common Era, They weren't just building barriers against the sea, they were inviting it in as a co-architect. Divers exploring these submerged ruins make an astonishing observation. Where modern harbor pilings show pitted, corroded surfaces, Roman concrete appears almost petrified, its outer crust roughened by waves but its core denser than the day it was cast. Core samples reveal why. Seawater percolating through the material over centuries didn't destroy it, it transformed it. The saltwater reacted with lime clasts and volcanic ash to form an intricate network of luminous tobermorite crystals, locking the concrete's particles together like microscopic armor. Modern engineers call this phenomenon reactive crystallization, but the Romans likely saw it as simple practicality. They built knowing the sea would make their creation stronger, not weaker. The harbor's design amplified this effect. Unlike today's solid concrete blocks, Roman piers used porous volcanic rock as aggregate, creating pathways for seawater to penetrate deep into the structure. This wasn't a flaw, it was a calculated strategy. As waves pushed mineral-rich water through these channels, chemical reactions deposited fresh layers of strengthening minerals along the interior walls. Contemporary marine concrete, designed to resist water infiltration, becomes vulnerable the moment cracks breach its waterproofing. Portus Cassinus's piers took the opposite approach. They welcomed cracks as opportunities for renewal, letting seawater trigger repairs on a molecular level. Recent studies at the University of Naples uncovered something even more remarkable. The concrete's outer layer, though worn by centuries of tides, acts as a protective skin, sacrificing small amounts of surface material to shield the core. Like a lizard shedding scales, this slow erosion exposes fresh mineral deposits that continue reacting with seawater, ensuring the structure never stops fortifying itself. Modern harbors require constant patching and coating to combat decay, but these ancient piers evolved their own defense system, one tidal cycle at a time. Perhaps the most telling detail lies in the harbor's construction timeline. Roman records suggest Portus Cassinus took decades to complete, not because of slow labor, but because builders understood their concrete needed time to cure properly. While today's contractors rush to finish projects within seasons, Roman engineers let their maritime concrete mature in controlled stages, allowing critical chemical reactions to unfold naturally. The result, a harbor that outlived its builders by 20 centuries, its submerged ruins now serving as both archaeological treasure and scientific Rosetta Stone. What makes Portus Cassinus so revolutionary isn't just its longevity, but its philosophy. Modern marine engineering wages constant war against the ocean, pumping water out of construction sites, sealing surfaces with synthetics, battling corrosion with toxic antifouling paints. The Romans worked with the sea's chemistry instead of against it. Their concrete didn't resist nature's rules, it rewrote them, turning corrosive saltwater into an eternal partner in preservation. As climate change accelerates coastal erosion worldwide, these 2,000-year-old piers whisper an urgent lesson. Sometimes survival means not fighting the elements, but learning their language. The disappearance of Roman concrete wasn't an overnight vanishing act. It was a slow unraveling, tied to the empire's own collapse. Picture the Mediterranean world in the 5th century, trade routes fracturing, skilled artisans dispersing, and the meticulous supply chains that delivered Pozzuoli's volcanic ash across provinces crumbling into disarray. Roman concrete didn't just require know-how, it relied on an intricate web of resources and expertise. Without the empire's vast infrastructure, the recipe became fragmented, then lost. By the time medieval builders attempted their own versions, they were working with echoes of a forgotten science, like trying to bake bread without knowing about yeast. One critical piece vanished first, the Pozzolana. This wasn't just any volcanic ash, it came from specific deposits around the Bay of Naples, where eruptions had created a unique blend of silica and alumina. When Rome's maritime trade networks collapsed, transporting this gold dust became impossible for local kingdoms. Medieval masons, unaware of its geological specificity, substituted whatever ash or sand they could find, with disastrous results. A 14th century chronicle from Canterbury Cathedral describes mortar that crumbled like dry cheese, a far cry from the indestructible Roman walls still standing nearby. Even when builders stumbled upon decent volcanic material, they lacked the Romans' precise lime slaking techniques, leaving their mixes brittle and prone to erosion. The deeper issue was one of broken knowledge transfer. Roman engineering wasn't just about materials, it was a system perfected over centuries and passed down through guilds and apprenticeships. As the empire's schools and workshops dissolved, so did the nuanced understanding of hot mixing, aggregate grading, and seawater curing. What remained were oversimplified legends, like the myth that Roman concrete contained animal blood or magic powders. Charlemagne's architects, attempting to revive Roman grandeur, produced lumpy imitations that cracked within decades. The stunning Abbey of Cluny, once Europe's largest church, used a weak medieval mortar that necessitated constant repairs, while the Roman amphitheater in Nimes, just a few miles away, stood untouched. Climate shifts exacerbated the problem. The volcanic regions of Italy became harder to access amid the political chaos of the Middle Ages, and the Little Ice Age altered water tables, making lime production inconsistent. But perhaps the most revealing clue comes from the Byzantine Empire, Rome's eastern successor. Though they inherited Roman engineering traditions, their concrete structures gradually declined in quality after the 7th century. Analysis of Constantinople's later walls shows a stark drop in aluminous tobermorite crystals, replaced by crumbly, hastily mixed fill. Even with the recipe theoretically preserved, the meticulous craftsmanship had faded. The final nail came with changing priorities. Post-Roman Europe valued speed and frugality over longevity. Cathedrals rose quickly to assert religious power, using cheap local materials rather than importing premium Pozzolana. The mindset had shifted from building for eternity to building for now. A 9th century monk's diary laments crumbling monastery walls, musing that the ancients must have bargained with angels for their secrets. He wasn't entirely wrong. Those secrets weren't supernatural, but they were irrecoverable without the empire's vast, interconnected machinery of knowledge and trade. By the Renaissance, when architects like Brunelleschi studied ancient ruins, they marveled at the concrete's endurance but couldn't decipher its alchemy. The Pantheon's dome inspired imitations across Europe, yet none replicated its material genius. The recipe wasn't just lost, it was stranded beyond reach, like a message in a bottle washed out to sea. By the time the Byzantine Empire rose from Rome's ashes, the secret to legendary concrete had already begun fading like a forgotten alchemy. Desperate to maintain Rome's architectural legacy, Byzantine engineers resorted to desperate measures, crushing old pottery and bricks as makeshift volcanic ash substitutes. At first glance, it seemed logical. Pottery like Pozzolana contained silica, but the results were catastrophic. Samples from Constantinople's Theodosian walls, once the mightiest fortifications in Europe, reveal a heartbreaking truth. Where Roman concrete formed interlocking crystals that laughed at siege engines, Byzantine mortar crumbled into sandy grit after mere centuries. The difference lay in chemistry. Roman Pozzolana's volcanic glass particles reacted explosively with lime, creating that self-healing binder. Pottery shards, though rich in silica, had been transformed by kiln fires into inert, unreactive ceramics. It was like substituting baking soda for flour. Similar appearance, disastrous results. The failures weren't immediate. Early Byzantine structures like the Hagia Sophia still incorporated remnants of genuine Roman concrete techniques, mixing in whatever Pozzolana could be scavenged from ruined imperial warehouses. But as supplies dwindled, compromises multiplied. A 9th century repair manual from Ravenna instructs masons to mix lime with ground tiles and brick dust as a last resort. Archaeologists studying these patches find telltale signs of decay, crumbling sections where the mortar turned to powder, leaving gaping voids between stones. The tragedy is etched in the ruins of the Blascherny Palace, where Byzantine emperors once held court. Its lower walls, built with true Roman concrete during Constantinople's golden age, remain intact. The upper additions, patched with pottery-laced mortar during the empire's decline, resemble eroded sandcastles. What the Byzantines failed to grasp was how precise Roman material science had been. Pozzolana wasn't just volcanic dirt, it came from specific eruptions where extreme heat created glassy, reactive particles. Crushed ceramics, though visually similar, lacked this geological spark. Without it, Byzantine concrete couldn't form the calcium silicate, hydrate bonds that made Roman structures immortal. Their walls still stood sometimes, but only through sheer mass, requiring monstrous thickness to compensate for weak mortar. Where Roman builders crafted slender, elegant arches, Byzantine engineers erected hulking buttresses, fighting physics with brute force rather than finesse. The consequences rippled across history. When Mehmed II's cannons battered Constantinople's walls in 1453, it wasn't the ancient Roman sections that fell first, it was the brittle Byzantine repairs. Modern laser scans show cracks radiating from medieval mortar joints like fault lines, while original Roman concrete absorbed the bombardment shockwaves. Even in defeat, Rome's engineering superiority endured. Today, as preservationists struggle to stabilize Byzantine monuments like the Chora Church, they face a cruel irony. The only mortar that bonds successfully with the ancient walls is modern concrete, laced with, you guessed it, Italian Pozzolana. After 1,000 years, the cycle completes itself. The empire's lost recipe still mocks its successors from the ruins, a silent testament to what happens when knowledge fractures faster than stone. The story of Roman concrete might have remained buried in ruins forever, if not for a determined British engineer named John Smeaton and a lighthouse crumbling into the North Sea. In 1756, as storms battered the Eddystone Reef off England's coast, Smeaton faced an impossible task: rebuilding a lighthouse that kept collapsing under the assault of waves. Traditional mortar, made with ordinary lime and sand, dissolved like sugar in the relentless saltwater. Then Smeaton stumbled upon an ancient text describing Roman harbors that thrived in seawater. Inspired, he embarked on a series of experiments that would unknowingly resurrect a 2,000-year-old secret. Smeaton's breakthrough came when he tested various lime mixtures by submerging them in seawater tanks. Ordinary mortar turned to mush within weeks, but one mixture held firm: a blend of hydraulic lime, a type that sets underwater, and Italian volcanic ash. He didn't realize it at the time, but he'd essentially recreated Roman concrete. The volcanic ash, imported from the very same Pozzuoli region the Romans had mined, contained the same silica-rich particles that made ancient marine structures indestructible. His rebuilt Eddystone lighthouse, completed in 1759, became the first major structure in centuries to harness Pozzolana's power, standing strong for over 120 years before being dismantled. Word of Smeaton's success spread like wildfire among European engineers. Suddenly, the crumbling Roman harbors they dismissed as relics became blueprints. In France, architects studying the ruins of Fréjus's ancient port confirmed that its mortar contained volcanic ash from the Massif Central, a local substitute for Italian Pozzolana. By the late 18th century, Roman cement became a buzzword in engineering circles, though its true chemistry remained a mystery. Builders mimicked the recipes without understanding why they worked, like medieval alchemists copying symbols without grasping their meaning. The real turning point came with the discovery of similar volcanic deposits beyond Italy. When British geologists found pozzolanic soil in Bavaria and the Rhine Valley, it sparked a continental hunt for natural alternatives. Thomas Telford, the visionary behind Britain's canal system, famously used crushed brick dust as a makeshift pozzolana, an echo of the Byzantine Empire's failed experiments, though with better results thanks to refined lime slaking techniques. The Industrial Revolution accelerated this revival, with factories mass-producing hydraulic cement for bridges, docks, and tunnels. Yet despite these advances, something crucial was still missing: the Romans' grasp of concrete as a living, evolving material. Smeaton and his contemporaries had resurrected part of the recipe, but not its soul. They replicated Pozzolana's binding power without unlocking its self-healing potential, producing concrete that was merely waterproof rather than regenerative. The difference became tragically clear in the 19th century, as early skyscrapers like London's Royal Aquarium began showing cracks within decades. Builders had the ingredients, but not the wisdom, the patience to let concrete cure slowly, the foresight to leave reactive lime pockets, the understanding that strength could grow with time. Looking back, Smeaton's lighthouse was both a triumph and a missed opportunity. He proved Roman techniques could work in the modern age, yet his successors prioritized speed over longevity. Today, as we relearn the value of slow-curing, mineral-rich concrete, his story serves as a reminder: rediscovery isn't just about unearthing old recipes. It's about rediscovering the mindset that created them, the respect for natural materials, the willingness to let time do its work, the humility to learn from ruins that have outlived every empire that tried to conquer them. The 20th century didn't just forget Roman concrete, it deliberately turned away. As the world rebuilt from two devastating wars, speed and cost became the holy grail of construction, and Portland cement, invented in the 1800s, seemed like a miracle. Its set fast required no rare volcanic ash and could be produced anywhere. The crumbling grandeur of Roman monuments became a footnote in engineering textbooks, dismissed as obsolete relics of a slower age. But in the race to rebuild, a critical oversight emerged. We sacrificed permanence for convenience, trading structures meant to last millennia for ones that barely outlived their builders. Portland cement's rise wasn't an accident. It was a product of industrialization's ethos. Factories could churn it out by the ton, and builders loved how it hardened within hours, not months. Skyscrapers, highways, and dams mushroomed across continents, their concrete skeletons rising at unprecedented speeds. Yet beneath this progress lurked a fatal flaw. Modern concrete strength relied on steel reinforcements, a marriage destined for divorce. When water inevitably seeped in, the steel rusted, swelling to 5 times its original volume and bursting the concrete from within. Roman engineers had avoided this trap entirely by designing compression-based structures that needed no metal bones. But 20th century architects, armed with calculators and confidence, dismissed their methods as quaint. The environmental cost of this shift remains staggering. Producing Portland cement demands roasting limestone at nearly 1,500 degrees Celsius, a process that spews roughly 1 ton of carbon dioxide for every ton of cement made. Roman concrete, by contrast, required no fossil fuels, just lime kilns heated by wood or charcoal and volcanic ash scooped from the earth. Modern concrete became the second most consumed material on Earth after water, yet its lifespan paled in comparison. The Pantheon's dome, built without a single watt of electricity, still shelters visitors today. Meanwhile, Boston's $2 billion Big Dig tunnels, completed in 2007, started leaking within a decade. The post-war infrastructure boom magnified these flaws. Governments poured money into roads, bridges, and housing, but shortcuts became the norm. Concrete mixes were watered down to save costs, and quality control often took a backseat to deadlines. The result, a ticking time bomb of decay. America's interstate highways, hailed as engineering marvels in the 1950s, now require constant, costly repairs. Japan's concrete seawalls, built to last a century, crumbled after 30 years of saltwater exposure. Roman marine concrete, meanwhile, grew stronger under the same conditions, its chemical reactions turning corrosive seawater into a strengthening agent. Perhaps the greatest irony lies in what we lost culturally. Roman builders saw concrete as a collaboration with nature, its slow cure and self-healing properties woven into their worldview. The 20th century treated it as a disposable commodity, valuing quick turnover over legacy. Today, as climate change exposes the fragility of our infrastructure, we're left staring at ancient Roman piers still standing in harbors while our own dissolve. The lesson isn't just about materials, it's about time. The Romans built with the humility to let their creations evolve. We built with the arrogance of immediacy, and the cracks in our cities are the receipts. The Romans built an empire without smokestacks. Their concrete strength came from chemistry, not coal. Unlike modern cement production, which pumps out nearly a ton of carbon dioxide for every ton made, Roman lime kilns operated at half the temperature, fueled by simple wood fires rather than fossil fuels. Even more remarkably, their key ingredient, volcanic ash, required no energy-intensive processing. Mother Nature had already done the work, baking the perfect pozzolana in the heart of volcanoes. Compare that to today's cement industry, responsible for 8% of global CO2 emissions, more than all the cargo ships and airplanes in the world combined. The terrifying math of climate change makes Rome's approach suddenly urgent again. If we're going to slash emissions while still building the cities of the future, we might need to raid the past for answers. Startups are already on the case. In a lab outside Austin, Texas, engineers at DMAT are mixing up a Roman-inspired recipe they call regenerative concrete. Instead of blasting limestone in coal-fired kilns, they use industrial byproducts like fly ash from coal plants, a nod to Rome's resourcefulness with local materials. The magic happens when these waste materials meet a low-temperature lime binder, creating a chemical reaction eerily similar to ancient Pozzolana mixes. Early tests show their concrete not only cuts emissions by 70%, but develops Roman-like self-healing properties when exposed to moisture. It's as if 2,000 years of concrete evolution have looped back to where we started with a crucial upgrade. This time, we understand the science behind why it works. Other pioneers are looking to the sea for solutions, just as the Romans did. California-based Blue Planet Systems mimics Rome's marine concrete by injecting captured CO2 into their mix, essentially turning greenhouse gas into a strengthening mineral. The process mirrors how Roman harbor concrete absorbs seawater to form durable crystals, except here, the sea is factory emissions locked away permanently in sidewalks and buildings. Meanwhile, in Italy, architects are going straight to the source, using Pozzuoli's volcanic ash to restore ancient aqueducts with mortar that's chemically identical to the original. The kicker, this restoration concrete has a carbon footprint 80% lower than modern alternatives. The real revolution lies in shifting our mindset from resistance to collaboration. Modern engineering treats concrete as a static product, mixed, poured, and forgotten until it cracks. The Romans saw their material as a dynamic system, evolving with its environment. Today's innovators are taking that philosophy further. Mining researchers recently developed a living concrete infused with bacteria that secrete calcite to seal cracks, a biological twist on Rome's lime-classed mechanism. Another team at Cardiff University embedded pH-sensitive microcapsules that release healing agents when water penetrates, creating a high-tech echo of Roman concrete's seawater reactions. What makes these experiments so compelling isn't just their technical cleverness, it's their humility. After centuries of assuming we'd outgrown ancient techniques, we're realizing the Romans held keys to sustainability we're only now beginning to grasp. Their concrete didn't just endure time, it worked in harmony with natural processes we've spent the industrial age battling. As climate deadlines loom, the urgent question isn't whether we'll return to Roman principles, but how quickly we can adapt them to modern scales. The Pantheon didn't need a carbon offset program. Its brilliance was baked into the recipe from the start. For a world drowning in concrete and emissions, that's a blueprint worth stealing. The same concrete that built an empire on Earth might soon pave humanity's path to the stars. NASA scientists are staring down one of their biggest challenges: how to construct moon bases without hauling tons of building materials from Earth, and their eyes keep drifting back to the Pantheon. It turns out lunar soil bears an uncanny resemblance to Roman concrete's secret weapon, volcanic ash. Those jagged, glassy particles in moon dust, they're packed with silica and alumina, eerily similar to the reactive ingredients in Pozzuoli's Pozzolana. Suddenly, a 2,000-year-old technology isn't just history, it's a blueprint for interplanetary survival. Engineers at NASA's Ames Research Center have been running experiments that would make a Roman builder nod in approval. They've created prototype lunar concrete by mixing synthetic moon dust with sulfur-based binders, mimicking the hot mixing techniques of antiquity. The results are startling. Just like Roman marine concrete thrived in seawater, their lunar version hardens in the moon's vacuum, actually benefiting from the lack of atmosphere. Micrometeorite impacts that would shatter conventional materials, they trigger localized melting in the space-aged concrete, fusing tiny craters shut like self-healing wounds. It's as if the Romans left us a cosmic cheat code, their material science perfectly suited for environments we've yet to colonize. The European Space Agency has taken this concept further with their regolith additive construction project. Instead of traditional molds, they're testing 3D printers that extrude moon dust concrete in layered domes, an echo of the Pantheon's gradual construction. There's poetic symmetry here. Just as Roman builders adjusted their concrete recipes for different environments, denser mixes for harbor walls, lighter blends for domes, lunar architects are tailoring their mixes too. High titanium soils near the moon's mare regions might require different additives than highland areas, mirroring how Roman engineers selected volcanic ash from specific quarries. The moon, like the Mediterranean, isn't a monolith. It demands localized solutions. What makes this research revolutionary isn't just the practicality, it's the philosophy. Modern construction assumes abundant resources, easy transport, and forgiving environments. Roman engineering, forged in an era of limited technology, shares DNA with space exploration's constraints. Both require building with what's available, designing for extreme conditions and planning for centuries rather than decades. When NASA tests lunar concrete's radiation-blocking properties, they're rediscovering what Roman builders knew instinctively. The best materials don't just resist their environment, they collaborate with it. A moon base made from local regolith could shield astronauts from cosmic rays, just as Roman concrete's dense minerals blocked seawater's corrosive touch. The implications stretch beyond the moon. Mars' iron-rich soil might work even better, potentially creating concrete that's stronger than Earth's through redox reactions we're only beginning to understand. Asteroid mining could unlock new varieties of space pozzolana, each with unique properties. This isn't just about avoiding billion-dollar payloads of Earth concrete, it's about embracing an ancient truth the Romans carved into their harbor ruins. Longevity comes from harmony with local materials. The Pantheon's dome survived because it wasn't just built for Rome, it was built of Rome. Our off-world structures will need that same symbiotic relationship. Perhaps the most humbling realization is how history's arc bends. The same empire that paved roads across continents may have unknowingly left us instructions for building interplanetary highways. As NASA prototypes sit in vacuum chambers, slowly curing under conditions that would horrify a modern construction crew, they're proving something profound. Roman concrete wasn't just advanced for its time, it was ahead of ours. The future of extraterrestrial architecture might not lie in glittering sci-fi alloys, but in rediscovering the alchemy hidden in our oldest ruins. When astronauts one day pour lunar concrete under Earth's glowing crescent in the black lunar sky, they'll be completing a circle started by artisans 2 millennia ago, mixing local dust with borrowed wisdom, building anew with ancient echoes. Attempting to recreate Roman concrete today feels like trying to bake sourdough with store-bought yeast. The ingredients might look similar, but the magic lies in details we're still learning to measure. Modern laboratories have every advantage: electron microscopes, precise scales, climate-controlled chambers, yet our best reproductions crumble where ancient samples endure. The problem isn't lack of effort, it's that Roman engineering was a symphony where even the silences mattered. Take Pozzolana, that volcanic ash cornerstone. Researchers in Switzerland recently discovered that not all Italian ash works equally. Only deposits from specific eruptions contain the right glassy, reactive particles. Modern builders often substitute fly ash from coal plants, but these industrial byproducts lack the mineral diversity nature perfected over millennia. Even when using authentic Pozzuoli ash, many experiments fail because they skip the Romans' most counterintuitive step: imperfection. Contemporary concrete mixes aim for complete, uniform reactions, every particle of lime perfectly bonded, no remnants left behind. Roman engineers did the opposite. Their hot mixing technique deliberately left pockets of unreacted lime, those tiny white flecks once mistaken for sloppy workmanship. These dormant particles became the material's immune system, activating when cracks introduced moisture. Modern recipes eliminate this variable, seeking total consistency. The result: concrete that sets predictably but has no capacity for self-repair. It's like removing all the white blood cells from a body to make it purer, only to wonder why it can't heal. The Romans weren't messy, they were microbiologists before microscopes, engineering resilience into the very flaws we've been trained to avoid. Then there's the seawater paradox. For decades, engineers assumed saltwater was concrete's nemesis until they analyzed Roman harbor samples and found chloride ions had penetrated 20 centimeters deep without causing damage. Modern marine concrete relies on steel reinforcements and waterproof coatings, creating a brittle dichotomy. Either water stays out completely or the structure fails catastrophically. Roman concrete embraced permeability, allowing seawater to percolate through intentionally porous aggregates. This wasn't a design flaw, it was a distributed network of mineral factories. Each time saltwater encountered a limeclast, it sparked new crystal growth. Current reproductions often use dense, impermeable aggregates, starving the material of this chemical dialogue. Even time itself works against modern imitations. A team in Naples recently cured test blocks for 3 years, far longer than industry standards, only to find that Roman-style concrete still hadn't developed the full crystalline network of ancient samples. The Pantheon's dome didn't reach peak strength in months or even decades. Its tobermorite crystals matured over centuries. Today's construction timelines can't accommodate such patience. We've optimized concrete to harden by the 28-day mark, trading long-term durability for short-term convenience. It's like comparing a microwaved meal to a slow-cooked stew. Both feed you, but only one develops depth. Perhaps the most overlooked factor is craftsmanship. Roman builders weren't following rigid formulas. They adjusted mixes based on a structure's purpose and environment. Maritime projects used coarse volcanic rock for better seawater interaction, while decorative elements incorporated fine marble dust. Modern reproductions often apply a one-size-fits-all approach, ignoring how the Romans tailored recipes like chefs balancing flavors. When researchers at Berkeley precisely replicated the mineral ratios from Portus Harbor samples, but used mechanically mixed mortar, the result lacked the layered microstructure of hand-mixed ancient concrete. The human touch, the rhythmic turning of trowels, the intuitive adjustments to moisture, left subtle gradients that machines can't replicate. This isn't just about resurrecting an old material, it's about confronting our industrial biases. We've spent 2 centuries optimizing for speed and scale, while the Romans optimized for time. Their concrete wasn't better because they knew more chemistry. It was better because they respected what they couldn't control. The slow curing, the reactive imperfections, the collaboration with seawater, these weren't compromises, but sophisticated negotiations with nature. Every failed modern reproduction teaches the same lesson. Sometimes durability means letting go of perfection and embracing the beautiful mess of natural processes. The irony is rich. We have satellites and supercomputers, yet our most advanced labs are still decoding the wisdom of laborers who mixed mortar with wooden paddles under the Mediterranean sun. The debate over Roman concrete isn't just about materials, it's a collision of philosophies. On one side, purists argue we should replicate the ancient recipes down to the last grain of Pozzuoli ash, insisting that any deviation corrupts the alchemy that made Roman structures immortal. These traditionalists point to restoration projects like the Trajan markets in Rome, where authentic pozzolana and hot mixed lime have revived 2,000-year-old walls with near-perfect fidelity. There's poetry in their approach, mixing mortar in the shadow of the Pantheon, using tools and techniques preserved in Vitruvius's scrolls. But romance aside, the challenges are stark. Importing Italian volcanic ash to build a bridge in Canada isn't just expensive, it's ecologically dubious. And let's not forget, the Roman Empire collapsed in part because its supply chains grew untenable. Are we really wiser to resurrect them? Meanwhile, innovators champion a hybrid future. Roman principles filtered through modern science. Startups like Solidia Technologies are reimagining the hot mixing technique with industrial byproducts, swapping scarce pozzolana for fly ash from coal plants. The result's concrete that cures with CO2 instead of emitting it, blending ancient wisdom with cutting-edge sustainability. Or take researchers at Drexel University who have engineered synthetic tobermorite crystals to mimic Roman self-healing, but with nanoscience precision. These adaptations aren't just practical, they're necessary. The world pours over 4 billion tons of cement annually, 20 times Rome's output at its peak. Scaling antiquities' recipes to modern demands without modification would be like powering New York City with olive oil lamps, yet compromises come with trade-offs. Purists warn that modern substitutes lack the mineral complexity of natural pozzolana, pointing to studies where fly ash concrete failed to develop the same crystalline networks. Innovators counter that perfect replication is impossible anyway. Today's limestone, seawater, even air pollution differ chemically from Rome's environment. And then there's the elephant in the room, labor. Roman concrete strength owes as much to craftsmanship as chemistry. The slow hand mixing, the patient curing, and those thrive in an era of union wages and shareholder deadlines. The Pantheon took years to build. Today's developers measure timelines in weeks. The cost debate cuts both ways. Authentic Roman mixes might save money long-term. Mighty estimates their lifespan could reduce reconstruction costs by 70%, but upfront expenses terrify budget committees. A single cubic meter of true pozzolanic concrete can cost triple standard Portland cement. Innovators argue hybridization offers a middle path, self-healing additives in critical structures like dams or nuclear containment, while cheaper modern concrete handles sidewalks. But purists shudder at the inconsistency. Would Roman engineers have built the Colosseum's foundations with good enough materials? Beneath these arguments lies a deeper question: what are we trying to preserve? The letter of the recipe or its spirit? Rome's greatest innovation wasn't a specific mix, it was a mindset of collaborating with nature rather than conquering it. Whether we achieve that through exact replication or clever adaptation might matter less than remembering why we lost it in the first place, the arrogance that newer must mean better. Perhaps the real lesson isn't in the ash or the lime, but in the humility to recognize that some ancient solutions weren't just products of their time, they were ahead of ours. Beneath the sun-baked hills of Pozzuoli, where the earth still whispers of Vesuvius's fiery past, miners descend into pits that haven't changed much since Roman ox carts hauled ash to build the Pantheon. The air here smells of struck matches and damp stone, a scent that clings to your clothes like history itself. Wearing hard hats instead of tunics, today's crews extract the same rust-red pozzolana that once cemented an empire, their excavators biting into strata that Pliny the Elder might have touched. But this isn't some relic frozen in time. It's a living laboratory where geologists in high-vis vests scrutinize each shovelful with X-ray diffractometers, verifying the volcanic ash's mineral signature against samples from ancient ruins. The irony is palpable. Modern science's most advanced tools are now guardians of a recipe older than the Colosseum. Walk with me through the quarry's terraced levels, where every layer tells a story. Near the surface, the ash is loose and powdery, perfect for blending into restoration mortars that must match 2,000-year-old patinas. Deeper down, the rock hardens into tuff, a natural concrete formed when volcanic debris fused under its own weight. Miners call these compacted layers the library, because each stratum preserves a different volcanic eruption like pages in a book. That one, the explosive Avellino event that buried Bronze Age villages. This banned ash from the eruption that terrified Romans in 79 of the Common Era, the same disaster that entombed Pompeii. The Romans weren't just mining dirt, they were tapping into a geological chronicle of catastrophe, turning apocalyptic events into architectural immortality. What's startling is how little the extraction process has changed. Sure, diesel loaders have replaced donkeys, but the real magic still happens at the sorting tables. Workers sift the ash through screens with the same rhythmic shaking motions depicted in frescoes at Herculaneum's ancient workshops. The foreman, a third-generation Pozzolana miner named Enzo, demonstrates how they grade material by grain size, coarse aggregates for harbor repairs, ultra-fine powder for delicate mosaics. The Romans knew, he says, rubbing a pinch between calloused fingers. The best pozzolana isn't just about chemistry, it's about texture, like flour for different pastas. Scientists from the nearby Campi Flegrei Observatory nod in agreement, their spectrometers confirming what Roman builders once judged by taste tests, literally. Ancient texts describe engineers chewing pozzolana to check its quality. A gritty crunch meant impurities, while a smooth melt signaled premium binder material. The real collaboration happens in a repurposed stone barn at the quarry's edge, where mineralogists and masons argue over coffee-stained blueprints. Here, a team from the University of Naples tests modern twists on the old recipes, substituting a fraction of pozzolana with recycled glass powder to reduce mining, or tweaking lime ratios to accelerate curing without sacrificing longevity. Their goal isn't blind replication, but evolution, preserving the material's soul while adapting to ecological realities. One wall displays core samples from famous Roman sites alongside their modern counterparts. The color matches so perfect you need a microscope to tell them apart. We're not just digging up the past, says Dr. Bianca Russo, a materials scientist. We're reverse engineering Roman wisdom to solve tomorrow's problems. She shows me a petri dish where seawater is transforming their test blocks, the same crystalline tobermorite needles that baffled Berkeley researchers, now growing under controlled conditions, proof that the ancient alchemy can be tamed. As dust stains the quarry terrace's gold, the day's last truckload rumbles toward a shipping container bound for an unlikely client, a nuclear waste facility in Sweden. Turns out Roman concrete's self-sealing properties make it ideal for sealing radioactive storage tunnels, where groundwater infiltration could spell disaster. It's a full-circle moment, the material that stabilized Rome's harbors now safeguarding humanity's most dangerous leftovers. The miners don't seem surprised. Pouring grappa into tin cups, they toast to the dust that outlives empires, their laughter echoing off walls that, like the concrete they enable, have learned the art of endurance. In Pozzuoli, the past isn't just preserved, it's still at work, one careful shovelful at a time. Ever wondered if you could whip up a batch of Roman concrete in your backyard? While we wouldn't recommend building your next patio with it, crafting a small, non-structural sample is surprisingly doable and a fantastic way to connect with ancient engineering firsthand. Start by hunting down the star ingredient, volcanic ash. If you live near a gardening store, check the soil amendment aisle for crushed pumice or scoria, often labeled as lava rock. These porous, lightweight fragments aren't identical to Pozzuoli's legendary Pozzolana, but they're close enough for a DIY experiment. Just avoid anything labeled perlite. It's been heat-treated into inert, popcorn-like balls that won't react like true volcanic ash. Next, you'll need hydrated lime, not the quicklime Romans used unless you enjoy caustic chemical burns. Hydrated lime, available at hardware stores as Type S masonry lime, is pre-slaked and far safer to handle. Mix 1 part lime with 2 parts volcanic grit in a plastic tub. Metal reacts with lime. Then slowly add water until it resembles thick oatmeal. Here's where things get fun. Unlike modern cement that sets within hours, your Roman-inspired mix will take days to stiffen. Cover it with damp burlap to slow drying. The slower it cures, the stronger the chemical bonds will form. For an authentic touch, toss in some aggregate like crushed terracotta, pottery shards, or brick fragments. Romans used these as fillers, and they'll give your sample a rough, rustic texture. But a word of caution, this isn't structural concrete. Without precise ratios and the Romans' hot mixing technique, your creation will crumble under real weight. Think of it as a historical artifact you can hold, a palm-sized tribute to ancient ingenuity. Watch for something magical around day 3. Tiny white flecks might appear. Those are lime clasts, the same self-healing agent scientists recently discovered in ancient samples. Sprinkle water on any hairline cracks, and you might witness a faint version of Roman concrete's legendary regeneration as the lime particles dissolve and recrystallize. It won't rebuild the Pantheon, but it's a mesmerizing glimpse into chemistry that's defied time. For the true alchemists, try a seawater test. Submerge a cured sample in salt water for weeks. A mason jar works perfectly. Check periodically if you're lucky. Minerals might form on the surface, mimicking the tobermorite crystals that strengthened Roman harbors. Just don't expect Instagram-worthy results overnight. Rome wasn't built in a day, and neither is its concrete's genius. This is hands-on history at its most tactile, a reminder that the ancient world's brilliance wasn't locked in scrolls, but in the very dirt beneath their sandals. Imagine a city where skyscrapers mend their own cracks after earthquakes, where underwater tunnels strengthen with each passing tide, and bridges develop thicker skin in response to heavy traffic. This isn't science fiction, it's the dawn of a new concrete age, inspired by 2,000-year-old Roman wisdom. Laboratories worldwide are racing to adapt ancient self-healing principles for tomorrow's megastructures, and the results could redefine how we live on this planet. Take earthquake zones like Tokyo or San Francisco, where scientists at the University of Michigan are testing concrete laced with limestone-producing bacteria. When tremors create microfractures, moisture activates these dormant microbes, triggering them to excrete calcite, nature's cement, that fills gaps within weeks. It's a biological twist on Rome's lime class system, with living organisms playing the role of microscopic repair crews. The real game changer lies beneath the waves. With sea levels rising, coastal cities are exploring floating neighborhoods and submerged infrastructure. Roman marine concrete's saltwater-activated strength makes it the perfect blueprint. MIT's latest prototypes incorporate glass capsules filled with sodium silicate, a modern analog to volcanic ash, that rupture when cracks form, releasing a healing gel that hardens upon contact with seawater. Early tests show these panels regain 90% of their original strength after damage, a feature that could make underwater cities like Japan's Ocean Spiral project feasible. Picture entire districts where concrete foundations grow more robust with each storm, their chemical makeup evolving like coral reefs. But the revolution isn't just about durability, it's about sustainability. The global construction industry accounts for nearly 40% of carbon emissions, largely from concrete production, Roman-inspired formulas could slash this footprint dramatically. Cardiff University's green concrete replaces 80% of traditional cement with engineered volcanic ash byproducts, cutting energy use by 60% while maintaining self-healing properties. Even more radical is the University of Colorado's photosynthetic concrete, infused with cyanobacteria that absorb CO2 while producing calcium carbonate, essentially making concrete that cleans the air as it heals itself. These innovations don't just reduce harm, they actively repair it, turning buildings into carbon sinks. The most ambitious applications lie in extreme environments. NASA lunar concrete research has taken cues from Roman harbor samples to develop mixes using Martian soil simulants. The red planet's iron-rich regolith, when combined with sulfur-based binders, forms a self-healing material perfect for pressurized habitats where cracks could be deadly. Closer to home, Canadian engineers are testing Roman-style concrete for Arctic pipelines, where traditional materials fail under freeze-thaw cycles. By leaving intentional lime pockets that activate when ice melts, their prototypes show remarkable resistance to the very conditions that crumble conventional concrete. What makes this research so thrilling is its democratizing potential. Unlike high-tech solutions requiring rare materials, many Roman-inspired concretes use industrial byproducts like fly ash or slag. A startup in India is already teaching rural communities to make earthquake-resistant homes using local volcanic soil and homemade lime, proving ancient wisdom can address modern inequalities. As climate change accelerates, these adaptable, low-carbon materials may become our greatest allies, not just in preserving infrastructure, but in reimagining our relationship with the built environment. The Romans built for centuries, we're learning to build for millennia. 2,000 years ago, Roman builders unlocked a trilogy of secrets that turned ordinary stone and dust into a material rivaling modern alchemy. The first key, Pozzolana, that volcanic ash rich in silica and alumina, capable of reacting with lime to form a glue stronger than time itself, but this was only the foundation. Their masterstroke came from embracing the enemy's seawater, where modern concrete corrodes. Theirs crystallized, transforming saltwater into a partner that wove mineral reinforcements to its very pores. And let's not forget their fiery technique, hot mixing quicklime directly into the mortar, leaving behind dormant pockets of reactive potential that could awaken centuries later to heal cracks like living tissue. These weren't just isolated tricks, they formed a holistic system, a philosophy of collaboration with nature's forces rather than domination. The Romans didn't have particle accelerators or electron microscopes, but their empirical brilliance lay in observing how materials behaved over generations. Pozzolana wasn't just added strength, it was a catalyst for chemical conversations that unfolded across centuries. Seawater wasn't a threat to mitigate, it was a reagent in an ongoing experiment. Hot mixing wasn't careless, it was foresight encoded into the microstructure. Together, these elements created concrete that didn't just resist decay, it evolved alongside it, turning stressors into strengths. Today, as our infrastructure crumbles under climate extremes and carbon budgets, this ancient wisdom offers more than nostalgia, it's a survival toolkit. Imagine flood barriers that fortify themselves with each storm surge, or carbon-neutral skyscrapers built from industrial byproducts, mimicking Pozzolana's magic. Researchers are already harnessing these principles to tackle radioactive waste storage, offshore wind farms, even Martian habitats. The irony is delicious. Our most advanced solutions might lie in relearning what builders in togas perfected millennia ago. So here's the challenge. What other forgotten technologies are hiding in plain sight, buried in ruins or faded manuscripts? Could Babylonian asphalt outlast our roads? Might Inca anti-seismic masonry save cities from earthquakes? The Romans left us a blueprint for longevity, but they weren't the only civilization to crack nature's code. Share your picks below, because the next revolutionary material might not be invented, it might just need reviving. The past is full of open secrets, waiting for curious minds to ask the right questions. Let's keep digging.